So right, this will be the first example that we're going to talk about in the topic of partial differential equation. So in the partial differential equation, or shortly known as PDE, we are going to look at a few types of equations that are very common in physics. So the first one that we are going to look at is the Laplace equation. So in order to look at this application of this Laplace equation, we are going to consider a case where you have a metal plate, and this metal plate, you have at one side a heat source, and then on the other side without heat source. So here you will have kind of like the area where you have a high temperature, which is where your heat source is. You are going to have a high temperature, and then as it goes along a direction, then this temperature is going to decrease. And we are going to look at a case in the middle of the plate where there is no heat source. So when there are no heat source, and that is when you can apply this Laplace equation. So if you are talking about a place, a location with heat source or any other sources, then you have to use another kind of equation, which is your Poisson equation. But let us keep that for the next few classes, and now we will concentrate on the situation where you have a metal plate without a heat source in the middle. So this is a kind of like a sketch, all right? So a sketch of the metal plate, which is here shown in red color. Here you have the source, where here you have T equals to 100 degrees Celsius, the temperature here, and then it's going to decrease along this y-axis. So we take this as a 2D plate, so there is no Z component. We are just only going to consider X and Y component. This metal plate, you have on the x-axis the width of the metal plate is going to be 10, let's say 10 centimeter, and then we are going to assume that the y-axis is going to extend infinitely, so you have a semi-infinite metal plate. So at this point here, your T is going to be equals to 0, and at the side of this metal plate, the temperature is also going to be 0 degrees, right? So here in the middle of this plate, as you've seen, there is no heat source, and therefore we can apply the Laplace equation. So in this case, the Laplace equation, I've written it as a nabla squared T xy. So the T here represents the temperature, which is going to change according to the x and y coordinates. So as I mentioned earlier, we're talking about a case without the heat source, and therefore on the right hand side here, this is equals to 0. So kind of like a refresh of what we are going to do is we are going to find an equation that relates the temperature with the x and y positions. Okay, so now we are going to write again the equation here. So this is Laplace equation, and this is a del operator, which we can actually write it in this way without the z component, because we are not considering the z axis in this case. And then right, so now we need to use the separation of variables. So we kind of like assume that the temperature is independent between the x and y axis, right? So we can write this equation. So here we are going to replace this equation to here, and then we are going to expand them. We will expand them, and you will get this equation over here. Okay, so notice there is a negative over here because this is a positive. So when you expand and you differentiate them, you are going to get a positive here, but then you move it to the right hand side, and then you have a negative sign here. So the whole point of this exercise is that here you will have on the left hand side a term which is related to the x only, and on the right hand side you have a term which is related to the y component only. So since the two are there is no dependence between the two of them. One is x and one is y. So you can the only time that you can have such a case is when these two are going to be equals to a constant. So in this case we can choose a constant. So here we choose it to be a negative k squared, right? So you can use any constant that you want, but here if you use negative k squared, you will see that the results is easier to interpret. You might ask, what happened if you don't write negative over here? So you are just going to equate the left and the right to k squared only. In that case, you have a slightly different situation. It can be applied to a different situation, but not to this case. But let us reserve that for later, and we will look at this case where you equate both left hand side and right hand side to negative k squared. So now when you have equate this to negative k squared, you are going to rewrite again. So you have the left hand side, this component equals to negative k squared, and this is the right hand side here equals to negative k squared as well. And then now what we need to do is we have to find a solution that fulfills this equation. So here you will see that this is the x part, the x component part. So the solutions that fulfill this equation is a sine and a cos. So sine kx and a cos kx. What you need to do if you want to satisfy yourself that this is true is just to simply replace, for example, sine kx into this equation, into the left hand side. So if you replace the sine kx to the left hand side, you differentiate twice, and you will see that this is going to give you negative k squared with the same function against sine kx, right? The same with the cos kx. Okay. Now we need to go to the next one, which is the y component, which is written here. So there is no more negative sign here because they are going to cancel one another. And in this equation, the function that fulfills this equation is going to be exponential ky and the exponential negative ky. So these are the two solutions that, actually four solutions that we will consider to solve this problem. So now I have written back the functions that we have obtained earlier. So on this this first parenthesis here is the solution for x, and the second parenthesis here is the solution for y. So here we have a sine kx and a cos kx, and this is going to be in exponential ky, exponential negative ky, and the combination of them is going to be the solution that we want. So in order to find which one is the one that we want, we have to apply the boundary conditions. There are a few of them, so let us look at them one by one here. So at the x equals to 0, we have the temperature to be equals to 0, right? So that is at the left hand side of the plate, left hand side left bottom of the plate. So here we need to use these two equations, so I'm going to put x equals to 0. So for x equals to 0, you have sine 0, which is equals to 0, and therefore this fulfills the boundary conditions. So this is going to be the function that we want. On the other hand, the cos kx, that is if you replace x by 0, so you see cos 0 is going to be equals to 1, and this is not the solution that you want, right? So here you rule out the cos function. So now let us look at the second boundary condition, that is when we extend the metal plate to infinity along the y-axis, the temperature is going to be equals to 0 here. So here you put back the y equals to infinity here into these two equations, and you will see the exponential k infinity, this is not going to be 0, this is going to be a huge number, so therefore this function is not possible. And for the second one, which is exponential minus k infinity, so this is going to be equals to 0, and therefore this is the solution that you want. So taking these two solutions, that is, this is for the x and this is for the y, you're going to combine them, and then you have the temperature T equals to sine kx exponential minus ky. And here there is one thing which you do not know, that is your k over here. So to find this k, you are going to apply the next boundary condition, that is x equals to 10. So this is on the right hand side of the plate. At x equals to 10, you have t equals to 0, right? So here this is very straightforward. You don't have to worry about the y, because at x equals to 10, that is on the right hand side, everything is going to be equals to 0. So you can skip this one, and you're going to look at this only. So here sine 10k x is equals to 10k, which where your x is equals to 10, then this is going to be 0. So this is true when your this term inside is equals to n pi. So sine n pi, whatever your n is, this is going to be 0. So therefore here you have k equals to n pi over 10. So now you have what you have done is you have used the boundary conditions to determine the coefficients k, as well as removing the two functions that you do not want. So at the end of these steps, you are going to get t equals to this expression here. So basically what you have done is to just replace the k by this value here. But then this is not the end, because if you look at this, there is one problem, that is when your y is equal to 0. So when y is equal to 0, our temperature is going to be 100 degrees Celsius, right? But then if you put in y equals to 100 over here, sorry, y equals to 0 over here, and you will see this is going to be equals to 1, and this is not equals to 100 as you wanted it to be. So then we have to think of a way to get a solution based on these two, and the idea is that you're going to use the Fourier series to actually get the solution that you want, that is at y equals to 0, you want t equals to 100. Right, so just now we have mentioned that this equation on the right hand side here, at the top of right hand side here, is correct, but then it is not fulfilling the last boundary condition, which is when y is equals to 0, my big T here, capital T, is going to be equals to 100 degrees. So this is not possible, because whatever your value of x is, this is going to be going to range from a -1 up to 1, right? So and then here when y is equals to 0, this is going to be equals to 1 as well. So there is no way that you're going to fulfill the condition where you have t equals to 100 over here. But then here you can use an idea from a Fourier series, that is, you are going to take a combination of different value of n in order to give the boundary condition that you want. So in order to use this idea, you are going to write it like this. So this equation over here. So notice that the sign and the exponential function is the same as what you have on the right hand side, except that now you have a summation sign and a bn. So b with a subscript n here is to say this is the coefficient. B is a Fourier coefficient for the n value, right? So you have b1, b2, b3, and so on. And this summation is simply taking the combination from n equals to 1 to a reasonable value that you want. Okay, so the only thing that you do not know now is the Fourier coefficient Bn here, and the way that you are going to find this will be explained in Fourier series, but then the idea, the implementation is rather straightforward. So what you need to do is you are going to multiply both left hand side and the right hand side by a sine function. And then here, before you go there, you actually put the y equals to 0, because this is what you want. Y equals to 0, and this term is going to be equals to 1, so it's not going to appear in the derivation. And then you are multiplying both sides with the sine function, but here you put the sine m pi over 10x on the left hand side, and this is the same on the right hand side. And then you're going to integrate both left hand side and right hand side here, and you will see that the n is going to take many values, but then there will be one value which is the n is going to be equals to the m. So when m is equals to n, then you will have the summation here will vanish, of course, and you will have a sine squared here. So you have a sine squared m pi over 10x on the right hand side. So the derivation is rather straightforward. You will know how to do this, and I leave this as an exercise for you. At the end of the day, you are going to get Bn equals to 400 n pi, 400 over n pi, and you just have to substitute this back into this expression here, so that now the temperature, the function, the temperature as a function of x and y, is going to be written like this. Okay, so this is the solution that you want, and what I'm going to do next is to show you how it looks like on a plot. Alright, so now we are going to plot the temperature distribution for the case where you have a hot plate. You supply the temperature or the heat at one part of the plate, one end of the plate, and here we are going to put the temperature of the heat source at y equals to 0. And then on the boundary of this uh, plate is going to be T equals to 0, so your temperature is equals to 0. And we have derived this equation, which we have shown on the screen now. So here we have to remember, when we derive this, we have to find the Fourier coefficients, and this equation is going to be valid for odd numbers of n, right? So your n is going to be an odd number. When you derive this Fourier coefficient, you actually see that when n equals to even, then this is going to be equals to 0. So now that let us do that. So in order to plot this, we are going to define our x and the y. So here I define x from 0 to 1 to 10, and y is going to be going from 0 to 30. So 30 is rather probably is small as compared to our assumption here, because we are talking about semi-infinite plate, right? But then for a plot, you will see that this is sufficiently large. Then I'm going to take the mesh. I'm going to make a mesh points from these values, and the next one is to have to define what is my n. So actually, when we are talking about a series, the larger your n, the better it is, right? But for the sake of discussion, we are going to use n equals to 3 first. Then we are going to plot this function t, and in order to do that, we need to do a loop, because your n is going to increase from 1 to 3. So here I'm going to put a for I1 to n, and my temperature is going to be T equals to this form here. So in fact, I need to define what is my first T here, because this is supposed to be 0. So when n equals to 1, this T is going to be 0. So after the first step of the calculation, I will have a value which will now replace into this, and then you have to calculate n equals to 2, and then you will have a new T, and then you go on. So this is actually the idea of a loop. So and for right, but here there is actually a mistake, because I need to define my t equals to 0 first before I actually calculate my loop here. So let me just finish this, and now we have finished calculating the temperature as a function of x and y. So now let us plot this and mesh. So you will see this is the temperature distribution that you see, right? So here this is my x-axis, so my source is going to be over here, with the temperature over here is going to be 100 degrees, and here you see this is 0, because that is our condition that we want. At the side here, the temperature is equals to 0. And then you will see, let me just change the view. So here you will see this is a very high temperature at the y equals to 0, and then it slowly dies off, right? Okay, so here what we are interested is the region in this area, right? We are not really interested in this region, because this the Laplace equation is not correct here, because we have not taken into account the heat source. But you will see that at this region, then this Laplace equation is good, because here we do not have any heat source here. So this is the distribution, and one more thing that we can do with this is to show, what is the effect if I increase my n. So let me just close this, and let me just now define a point on the plate, right? So let's look at the x equals to 5 and y equals to 5. That is, this is going to be in the middle of the plate. So x and y is actually the x and y. It's just that in order to make a plot, we need to use the mesh points, right? So I'm going to use x equals to 5 and y equals to 5. And I'm going to first use n equals to, let's use n equals to 1. So again, I have to repeat this. Well, I make a mistake again. So I need to define t equals to 0. And then only I do my loop. So let me see. Right. So let me just, and t is 4. So I'm going to do my calculation again. I'm removing the semicolon so that we can see the value later on. Right. So here at the x equals to 5, y equals to 5, and n equals to 1, I have temperature at this point to be 26.468. Right, so now let me just increase my n. So now I'm going to increase my n to 3. I'm going to have to define t equals to 0 again, and then I'm going to do a loop, right, and in force to close the loop. And here you see my my temperature is going to be decreasing, so this is n equals to 1, this is n equals to 2, this is n equals to 3. So there is a decrease when you go from n equals to 1 to 3, so this n equals to 3 is better. But what happens if now we go to n equals to 5, right? So now if let's say n equals to 5 and we put t equals to 0 again, and now we continue with our loop, and finally we have this, then you will see, right, this is n equals to 1, n equals to 2, 3, 4, 5. So n equals to 1 to n equals to 2, you see there is no difference because in this case, as I've mentioned, our function is going to be valid for odd numbers of n, right? So that's why there is no difference in going from n equals to 1 to 2. But then n equals to 1 to 3, there is a difference. And then after that, we see increasing n is not going to change the results much. So here at this point, we can say the temperature to be equals to 26.1 degrees Celsius at x equals to 5, y equals to 5. Right, so this is the results that we have when we assume a semi-infinite plate with source supplied at one end of the plate. And we are going to look next into a situation which is more physical. That is, we will look at the plate which is finite, and we have to consider a solution which is slightly different than what we obtained here. So that's all for this video, and please go through this video if you need to. Make sure that you are very familiar with the idea, that is, for example, the separation of variables and how you obtain the Fourier coefficients and so on. So till then, so see you.